JPL's EELS robot, otherwise known as the Exobiology Extant Life Surveyor, is designed to travel down crevasses and moulins and glaciers using a unique corkscrew propulsion mechanism. The fluid underneath these glaciers is vital for furthering scientific understanding of subglacial environments. The liquid collected from these environments will be used to advance Earth and planetary science by determining how glaciers are formed, and future advancements could potentially lead to the discovery of life outside our planet. These glaciers are extremely difficult and dangerous to access for humans, so the EELS robot is a safer way to access glaciers on Earth and eventually Enceladus. Enceladus is an ice-covered moon of Saturn, and in a few short years, JPL hopes to reach Enceladus and analyze the subglacial environments there. Our goal is to help in this mission by designing a liquid sampling system and characterization system at various pressures and depths that is integrated into JPL's EELS robot. And with that, we're Team Galaxy Snake Cadets. Our team consists of 5 mechanical engineers, Annabelle, Colin, Catherine, Kinjal, and Henry, and we created a unique, easy-to-use liquid sampling system.
We analyzed the customer needs and engineering requirements to come up with some design constraints and specifications. The main requirement of the system was to be able to collect 1.4 liters of sample in under 15 minutes. The sampling system must be able to fit within the existing EELS robot segment, a 50 by 10 centimeter cylinder, and additionally, due to the corkscrew motion of the robot, the system cannot impede the motion of it by being too heavy or extending beyond the shell. Enceladus is extremely cold, and so the system must be able to withstand temperatures up to negative 200 degrees Celsius without experiencing electronic failures or allowing the sample to freeze. If the water freezes or becomes contaminated by the external sample or debris, the scientific findings will be rendered useless. The system must be properly sealed to prevent leakage, which would harm the sample and the electronics.
To achieve these design goals, our team created multiple designs that encompass different sealing and collection methods. We eventually landed on our final design, which meets all the necessary requirements. Throughout the iterative design process, it was determined to achieve the necessary flow rate at depth a pump was necessary. This presented a challenge as the design space is small and most traditional pumps within the necessary power requirements were too large. This led us to a peristaltic pump. Traditionally used in administering IV fluids, these pumps are compact, powerful, and have the ability to collect specific volumes, perfect for collecting precise samples. The water flows through a tube and is pumped to the medical-grade sterile IV bag with one-way flow capability. This prevents the sample from contamination and aids in preventing leaks. To monitor potential leaks, a leak sensor was incorporated into the design, which measures the humidity in the segment and can determine if there is free liquid inside it. Additionally, there are 2 temperature sensors and 2 pressure sensors on the exterior of the shell, which are able to characterize the exterior environment. This allows the sample to be taken at known temperature and pressure characteristics and gives a temperature and pressure history of the sample during travel. Now that the sample has been successfully collected, it needs to be easily removed for analysis. The testing prior to launch to Enceladus will take place on Antarctica, and while not quite as cold as Enceladus, Antarctica's surface reaches temperatures of negative 50 degrees Celsius. Therefore, the sample needs to be quick and easier to remove while wearing gloves. Our solution was a slide-out tray connected to a push-seal O-ring. It doesn't require dexterous or precise movement to operate, and it gives easy access to all components in the system. The tubing is attached to a quick disconnect, which are fast to remove and replace, and the pump is able to be opened to remove the tubing. This makes the sample removal process as seamless and quick as possible. The tray also allowed for separation of the main components using plate separators. This protected the electronics and the pump in case of a leak and prevented the sample's sterile bag from moving during travel. An initial prototype was created to validate our design and test the sealing capabilities of it. It uses PVC pipe as the exterior shell and a 3D printed tray. The ends of the tube were sealed using a screw tightening O-ring seal. The chosen pump was able to successfully pump 1.4 liters of sample in under 15 minutes, and the pressure and temperature sensors were able to accurately read the environment. The sealing and efficacy of the design were tested at depth. When submerged into the CRC's dive pool at 17 feet, the prototype did not leak and the interior remained dry. FEA analysis was done on the outer shell to determine the strength of the design while accounting for temperature effects and impact forces resulting from motion. This demonstrated that our chosen material of stainless steel is strong enough and will not fail during use. Additionally, thermal calculations were done to check the temperature of the inside air. It was determined that the temperature of the interior air will be approximately the same as the exterior air, leading to the necessity of a heat source or insulation. The motor for the pump was investigated, but creates a negligible amount of heat. While a successful prototype was created to meet the Antarctic conditions, additional work is necessary to prepare for Enceladus. This includes adding controls to sample at specific temperatures and pressures and manufacturing a space travel and Enceladus prepared system with a stainless steel exterior and higher quality sensors. Additionally, the prototype needs to be adjusted slightly to fully integrate into the EELS system. One end will be permanently sealed with an access hole for the power cable, and the other end will incorporate a more robust sealing mechanism. This has been Team Galaxy Snake Cadets. We'd like to give some special acknowledgement to our mentors at JPL, Kaylin Carpenter and Tom Nordheim, and our Georgia Tech advisor, Dr. Harris. Thank you so much.